And okay, so we're now recording, and let me go ahead and pull up my whiteboard here. And I got to make sure we're sharing, and we're going to share content. And so hopefully everyone sees the little girl, and here comes the whiteboard. Alrighty. Alright, so let's get started here. So far on this chapter, besides some definitions and such, the real mathy kind of stuff, and we should be practicing with balance equations and things like that, is so far we have 6.022 times 10 to the 23rd molecules or atoms for every something that's called a mole. And we're going to use this whenever we see the words atoms or number of atoms or molecules. That's when we're going to use this, because we're going to go by keywords. This is the way I try to do this. We go by keywords to figure out what we need, and then we set things up so that units cancel. That's how we do these. Okay, so we have this relationship right here. And we also have, and I want to throw this down here, let's say that we have something like this, C3H8, otherwise known as propane. Same stuff in propane heaters and things like that. That's propane. Okay, and I want to know something along the lines of how many moles of, say, carbon for every mole of propane. Okay, and what I'm going to say right here is, remember what I said when I said over here, I said 4 aluminums plus 3 oxygens. This is going back to Friday. 2 aluminum oxides, and I said we could say it was 4 atoms aluminum to 3 molecules oxygen gives you 2 aluminum oxides. But we said, you know what, that's too much trouble. We're going to say this is 4 mole aluminum, which is an awful lot of aluminum atoms, gazillions and gazillions, 10 to the 23rd, plus 3 moles of oxygen gives me 2 moles of aluminum oxide. Well, if you look at this formula here for propane, this actually means 3 mole carbon for every 1 mole C3H8. That's what it means to be C3 in C3H8. You have 3 mole carbon for every 1 mole of the whole molecule. You got 3 for every 1. And the same thing here. What does this mean right here? This means that we have 8 mole hydrogen for, guess what, every 1 mole of propane. Okay, so I'm showing you this because when we say that we have this molecule here, what we're really saying is that this is 1 mole. This represents 1 mole of C3H8. That's what it represents. For every 1 mole, you have 3 moles of carbon. For every 1 mole, you have 8 moles of hydrogen. Okay, and so this ties into a question that looks like this: how many mole carbon atom in 0.5 mole C3H8? Okay, now if you look, we're going from moles to moles. Okay, more on that in just a minute, but I just want you to get used to the idea here is that this is what that formula means. Okay, and so we're going from atoms to from propane molecules to carbon atoms. We're not being asked how many carbon atoms. We're asked for how many mole carbon atom. Very important distinction, because up here this is number of. Okay, and so we would say, this is how we would do this. We would say, well, we have 0.5 mole C3H8, all right, and then for every let me circle this in green. For every one of these propanes, you have 3 carbons. And so you would say 3 mole carbon for every 1 mole C3H8. And look, moles carbon is right there, and I didn't mean to cancel that, by the way. Let me just redo that. I didn't mean to cancel that. Mole carbon, and then look down here. We have moles C3H8 propane, and that does cancel. See? It cancels. And what are you left with? Moles carbon. And so 3 times that would give me 1.5 mole carbon. 1.5 mole carbon. Okay? Now, when we did this, what did we see? Here's where we go to. Let's try to understand the process of what just happened here. Okay? What happened here, I was asked how many of something was in something else. So the something is carbon atoms and the something else is propane. Or you can say the something was propane and the something else was carbon atom. But they are 2 different things. In other words, carbon atom is different from propane. Everybody agree that those 2 things are not the same thing? And they're not, okay? They're not the same thing. So here comes our next relationship. Okay, here's our next relationship. So what we're going to have is something called a mole ratio. A ratio is just a fraction. You know, like 2 to 3, 4 to 2, 1/3, 5/5, whatever. That's just a fraction. That's what a mole ratio is. And it's going to be mole of A over mole of B. Okay, and it's a ratio. It's not an actual number of moles. In other words, we're not going to say like 0.321 moles of whatever. That's not part of the mole ratio. And we're going to use this when we go from one thing to another. This is what we're looking for, one thing to another. And just to be complete, I'm going to put down here 6.022 times 10 to the 23rd of atoms, molecules per mole. And this was if we see number, let me write that a little bit better, number of atoms or molecules. Okay? Now these are, you can paraphrase these 2 things as being questions when I look at a problem, because going through a word problem is as much of anything as a skill. It's a skill. It takes practice. And here I'm going to tell you, I'm going to show you how to do word problems. And one of the ways of doing chemistry word problems is you ask yourself a series of questions and you answer these questions, and these questions provide what you need to solve the problem. So we have 2 questions so far. Do I see number of molecules or atoms anywhere in the problem? That's one question. And the second question is, do I see myself going from one thing to another thing? And if the answer is yes, then you use, for instance, number of atoms or molecules, you use that 6.022 times 10 to the 23rd per mole. And if the answer is yes, you're going from one thing to another, you use the mole ratio between the 2. And if the answer is no, then you don't use them. So it's a very affirmative sort of thing. It's like it's either yes or no. It's very binary. It's up or down. You either use it or you don't. So let's take a look at a problem here. So let's do a problem. Keep in mind these keywords up here at the top. And so I would say, so how many H atoms in 0.500 mole, let's go for C4H10, which by the way is butane, is the name of it. I'm just putting the names out here, not that you're necessarily responsible right now for the names, but understand, everything has a name. Everything has a name, just like you have a name. Everything has a name, okay? And so I look at this problem, and the thing about chemistry problems is you should avoid going straight for the setup. All right? I mean, I've done this enough, and eventually I hope that you will have enough practice that you could go straight to the setup. But right now, most of us are not ready to go straight for the setup. There are intermediate steps. So let's do the intermediate steps. So I'm going to change colors here to blue, and I'm going to look through this problem, and I'm going to look for keywords and key phrases. This is how you solve chemistry word problems. And so I look here and I see how many atoms. This tells me I need, and I'm going to number these, equation 1, equation 2. And that tells me I need equation number 2. I need that relationship number 2. So let's just copy it down. 6.022 times 10 to the 23rd H atom for every mole H atom. All right, now I'm not doing a setup. I'm just pulling down what I need based on keywords in the problem. Okay, so I got how many H atoms, and now I also look over here that I see that I am going from one thing to another thing. How do I know? I am going from between mole C4H10 and H atoms. They are not the same thing. So what's the relationship between the two? Well, I know there's 4 carbon moles, carbon atoms for every 1 mole of C4H10, and I know that there's 10 hydrogen atoms for every 1 mole of C4H10, right? So what are we after? We're after the H, moles of H for every C4H10, because we're going between moles. But where's the other moles? Well, we don't have moles, and that's the point I'm trying to make here. You're not looking for moles to moles in the problem. What you're looking for is 2 things. What are the 2 things? H and C4H10. So I would say, trust me on this, we say 10 mole H for every 1 mole C4H10. And let me make that look more like a 10. There it is. Okay. And so there's only 2 questions so far. There are going to be more, but so far all I've given you is 2 questions to ask, and I've answered both of them. Do I see H, how many H atoms? Yes, 6.022 times 10 to the 23rd per mole. Do I see going from one thing to another? And notice that I use the word thing. I don't say moles to moles, atoms to atoms, whatever. I just say, do I have one thing, am I going to another thing? And the answer is yes, and I write it out as a mole to mole. All right? And so I've answered both these questions, and the answer to both of them is yes, there is something going on. So what do we do now? We're done collecting everything we need, and we draw a line. We draw another line. What goes here is our measured number. Where's our measured number? This over here, which I'm going to put in purple colors, this is my measured number. All right, everybody agree? 0.500 moles, that's a measured number. It's something I had to measure. All right, all this other stuff on the bottom left-hand side, those are conversions that I pulled from the problem. All right, and so I put down my measured number. What's my measured number here? It is 0.500 mole C4H10. Sorry, I kind of ran out of a little bit of room there. And now, what do? This is your essential skill when you're doing these problems. Once you got everything you need from the problem, you have to be able to match. Do you know what it means to match? It means red with red, blue with blue, one with one, centimeters with centimeters, atoms with atoms, moles with moles. That's what I mean to match. And what do we match here? We match right here. The moles should go right there, shouldn't it? And so where do I see mole C4H10? And I look over here and I look, and it's right there. There's my C4H10. So this whole thing right here, because it matches, you see, needs to go over there. Now, it looks like since mole C4H10 is already on the bottom, I don't have to do anything to it. I don't have to flip it, but don't ever be afraid to flip it over. And so I go ahead and put it over here, and I say 10 mole H. And there it is. Okay? And so mole C4H10 cancels. And so remember, don't forget here, let's remember to do this. When you are done with one conversion factor, go ahead and put a check mark by it. That way you don't accidentally reuse it, because it's possible to accidentally reuse them. But you put a check mark by it. Now what do I do? Well, let me change colors here. Now, what needs to go down here? The unit that needs to go here is mole H, or moles H atom. It doesn't matter whether you say H or H atom, but we understand. And let me go ahead and label this with atom, because that's really what we're doing. And so where do I see H atom? Moles H atom. Well, we already used this one over here on the right, but here it is right here. There it is. Nope, sorry, excuse me. It's Monday and it's early. Hold on. H atom, H atom. It's right here. Here it is. There it is. Okay. And we look over here, and sure enough, that's where it goes, and we don't have to flip it or anything. And so let's go ahead and use it. And we're going to say 6.022 times 10 to the 23rd H atom for every mole H atom. And moles H atom cancels, and we're left with what? H atom. What are we looking for? How many H atoms? Do you see how that worked? Once I pull down based on these two questions, everything else after that is matching. You just have to be able to match. And once you match, in other words, you have all the units cancel. Now all I have to do is put it in the calculator. And I pull out my calculator and I go, let's see, 0.5 times 10 times 6.022 second E 23. And I get a number that makes sense, and that is, let me put it down low here so we can see it. Let me do it in blue. And the answer that I get is 3.011 times 10 to the 24th H atom. Now we have to do, what else do we have left here? We have significant figures. So I'm going to do significant figures. Let me do this, even though I'm just running out of colors. Let me do significant figures in red. We have 3 SF here. Leading zeros don't count. Trailing zeros do with a decimal. So that's 3 SF. This is counted, so it doesn't count for significant figure purposes. 1, 2, 3, 4, 5, that's counted, so it doesn't count. And this right here is 4 significant figures. And so our answer should have what? 3, none, and 4 means our answer should be 3SF, which means our final answer should be 3.01 times 10 to the 24th with significant figures. That's 3SF for this. Okay, so our answer should be 3SF. at the very end. Alrighty. Okay, so we've gone through this. So let's recap here. We have two relationships so far. We have a mole ratio, we have Avogadro's number. Okay, and two questions that we can ask each other. Okay, let's do one more of this, and this is just something that's kind of something that shows up on homeworks and quizzes. By the way, stay on top of your due dates for homeworks and quizzes. I don't like when people miss these things. All right, so let's see. Let's do another one. So let's say how many mole, let's say oxygen in 1.68 times 10 to the 24th atoms, well, let's say molecules of CO2. All right, so how do we tackle something like this? Well, we have two questions that we can ask ourselves so far. One is, do I see number of molecules or atoms? Well, I think so, because if I look up here, what do I see? I see a bunch of molecules of CO2. So sure enough, I should say 6.022 times 10 to the 23rd molecules CO2 for every mole CO2. Do I see myself going from one thing to another thing? And I do, because oxygen and carbon dioxide are not the same thing. And so we're going between these two things right here. And so I would say that we have 2 mole oxygen for every 1 mole CO2. And oh, by the way, if you decided to do this while I'm thinking about it, if you said 1 mole CO2 for every 2 mole oxygen, that is okay. All right, it's okay. It doesn't matter which one you put on top, which one you put on the bottom, because you're going to decide whether you're going to use it like it is or flip it over when you do your problem. Okay, so we've asked both questions, and the answer is yes to both. It could have been an answer, could have been just one to one or the other. And so we draw a line, another line, and we start with our measured number. Here we go, 1.68 times 10 to the 24th molecules CO2. Okay? Now, we have to cancel molecule CO2. So where do we see molecule CO2 up there? We see molecules of CO2 right there. And so this is the one that we're going to have to use. Now, we're going to have to flip this over to get molecules on the bottom. So we say mole CO2 for every 6.022 times 10 to the 23rd molecules CO2. There it is. And molecule CO2 cancels. There it is. All right, so I know I have it set up so far, and if we stopped here, we would have mole CO2. But that's not what we're after. What are we after? We're after mole oxygen. Now, where do we see mole CO2 in what we haven't check marked? And that would be right here. I see mole CO2. Why do I need mole CO2? Because I need mole CO2 here. See? And so I'm going to use this like it is, and I'm going to pull it down, and I say 2 mole oxygen, 2 moles oxygen for every 1 mole CO2. And I check and I see, and sure enough, moles CO2 cancels. I'm left with moles oxygen. Now, what would you do if you accidentally, if you cancel it and you couldn't cancel? Well, that just means you have to erase what you got and flip it over. All right, that's all that means. So you should always check. There's nothing worse than setting up a problem thinking you have it, but you don't check and make sure units cancel. You have to make sure units cancel. If you do make sure units cancel, then you know if they cancel, then sure enough you have the answer that you're looking for, which is right up here. Now all we got to do is put it in our calculator. So everybody, if you have your calculator, you ought to be using it. 1.68 second exponent 24 times 2 divided by 6.022 second exponent 23, and I get 5.5795. Whoops. 5795 and some numbers. And this is moles oxygen. How do I know it's moles oxygen? Because moles oxygen is the last number left. All right, now if you get, well, before I say anything about that, let's do significant figures. So what do we have here? We have 3 significant figures here. We have 4 significant figures there, and this is counted, so it doesn't count for significant figures. Only measured numbers count for significant figures. And so we go 3 and 4, so our answer should be 3SF. We go by least number significant figures. We count over. We go 1, 2, 3. We look one more over, and we have 5.58. 5.8. Yeah, 5.58 mole oxygen with significant figures. Okay, now to what I started to say here. Now let's say you got some weird number like times 10 to the blah blah blah, something really big or something really small. Then that's a calculator problem. All right, that's a problem with using your calculator, and you should get with me after class today that I can show you how to use your calculator properly. Okay, so you should have gotten 5.5795 with some numbers, but no exponents. Okay, there shouldn't have been an exponent. If you have an exponent, it's because there's a problem over here. All right, and I will help you. Just make a mental note. After class, I will help you with your calculator. All right? And there's usually at least a couple of folks who, you haven't done this before. It's okay. All right. All right. So this was sort of interesting. We can start out with some bazillion number of molecules of this and that, and I can tell you how many moles you have or how many atoms you have or whatever. Okay. All right. Now, interesting from just a mathy sort of standpoint. Now, the truly useful stuff I'm going to show you right now. So what do we have so far? Have we done molar mass yet? I don't think we've done molar mass yet. So let's do molar mass. Okay, so we have something called, we're going to switch gears completely here for a minute. We have something called molar mass, and that is the grams per 1 mole of something. And this is very important. Molar mass is always for 1 mole and only 1 mole. Only 1 mole, okay? All right, keep that in mind. All right, how do we calculate molar mass? What you do, molar mass, you use the periodic table. And what you're looking for is if you see grams, you see grams. This is our keyword. This is what we're looking for, right? How do we find it? We use the periodic table. When do we use molar mass? Is anytime you see grams. Anywhere in the problem you see grams, we're going to use the molar mass. Let me erase this stuff that in red here because I want to make some room here. Alright. Alright, so molar mass, how do we calculate it? Let's start with, if you look underneath carbon, you will see 12.011, and you will also see a 6 above it, right? This number right here is what we're going to use for our molar mass. And generally you want to use 1 or 2 decimals. Okay, in other words, you want to use 12.0 or 12.00. Oops, pardon me, 12.01. Okay. Now usually when I'm going to use this for a molar mass, usually I just use one decimal. Usually I say 12.0. If you use 12.01, you're okay. Matter of fact, if you use 12.011, you're okay. But you want to use at least 1 decimal. Okay? And so if we had something, say, like aluminum, it would be 27.0 is what I would use. Or say oxygen, I would use 16.0. Or chlorine, I would use 35.5. And what I'm doing is I'm just rounding the number that's underneath the element that's on the periodic table, and I'm rounding it to 1 decimal. Okay? Now, this number you're going to use is going to be per mole. So that's grams per mole. Grams per mole. Okay? And this up here becomes 12.011 grams per mole. All right, that's what happens. All right, now let's figure out the molar mass of a couple of things. Let me show you how it works. Okay, let's start with, say, aluminum oxide. And I want to calculate the molar mass of this guy. What is the molar mass? Okay, molar mass. So how would we do this? What we do is we say aluminum, let me just copy this back down here again. Aluminum oxide, what we would say is 2 times 27.0 grams per mole. Okay, and that is the 2 aluminums, and this is the aluminum right there from our periodic table. Then we would say plus 3 times 16.0 grams per mole, and that's the 3 from the oxygen, see? And then the oxygen itself is 16.0 grams per mole. Now, once you add all these up, what do you get? You get 102.0 grams. Now, we're not going to just say grams per mole, which is what it is. We're actually going to say grams aluminum oxide for every mole aluminum oxide. It is important to tag these guys. This is your tag. Tag them. Okay, make sure you tag them. It's not just, and make sure you use units. Your unit is not just grams, it's grams aluminum oxide. Your unit's not just moles, it's moles aluminum oxide. And your molar mass is not grams, it's grams per mole. The two go together. The two go together, all right? So be very careful that you're always using units. Okay, always use units. Be very careful that that's what you're doing. All right, so let's see if we can do some more here. Let's figure out some molar masses. So how about O2 gas? What's the molar mass of that? And a common mistake is just to go to the periodic table and say, well, that's 16. But keep in mind, what do we have here? We have a 2. And so that means 2 times 16.0 grams per mole, because there's your oxygen right there. And that is 32.0 grams O2 for every mole O2. Let's say we were trying to do, let's do calcium sulfate. This is calcium sulfate. You name the metal, calcium. You name the polyatomic, that is sulfate. And by the way, if you don't know these yet, that's on page 66. Okay, so what would we do there? Well, we look at our periodic table, we find calcium. Calcium is 40.078, so this is 40.1 grams per mole. Plus sulfur, sulfur's 32.1 grams per mole. Plus the 4 oxygens at 16.0 grams per mole. And now we can add them up. And so we go 40.1 plus 32.1 for 4 times 16, and I get 136.2 grams calcium sulfate for every mole calcium sulfate. And generally, when you're doing these molar masses, don't worry about, don't think too hard about significant figures for the answer. Just make sure you go out your 1 decimal. Because if you think about it, these are all 1 decimal, 1 decimal, 1 decimal. What's the rules for addition? Go by least number decimal places. So that's our molar mass for calcium sulfate. Okay. So this is an essential skill, is to be able to calculate your molar mass. Okay, and you always have a periodic table in front of you to allow you to do the molar mass. So let's go back over here and let's do some molar mass exercises, and then we're going to put it all together into one big equation. So we have molar mass, and the molar mass is grams per mole, and we're going to get the grams from the periodic table. And when are we going to use molar mass? We're going to use the molar mass anytime we see grams. Anytime you see grams, you're going to use a molar mass. This is our keyword. So let's do a couple of molar mass problems, and then we're going to put everything together with all that we have. All right, so let's say that we have, let's say, how many mole is 14.6 grams aluminum oxide? How many moles is 14.6 grams aluminum oxide? And so for any problem that we're doing, we have to ask ourselves some questions. We don't want to jump straight to the setup. And so the first question I ask myself is, do I see number of atoms or number of molecules? And the answer is no. I don't see anything about atoms or molecules or how many we have in this problem. Okay, don't need 6.022 times 10 to the 23rd. Second question we ask ourselves is, do I see myself going from one thing to another? And the answer is, well, no. The only thing that we have up there is aluminum oxide. We're not, for instance, we're not going to oxygen, we're not going to aluminum, we're just have aluminum oxide. So the answer is no for that one as well. Do we see grams? And the answer is, why, yes, we do. I see grams aluminum oxide. So what do we see up here? Anytime you see grams, you need the molar mass. Now, we need the molar mass of the aluminum oxide, and that is, of course, 27.0 times 2 plus 3 times 16.0. I'm getting these numbers off the periodic table, and it's 102.0 grams aluminum oxide for every mole aluminum oxide. Okay, I went through. I know you got to understand here, yes, we're doing molar mass right now, but you still have to ask yourself these questions every single time you do a problem. Don't sacrifice your principles for a little bit of expediency. All right, so I have this. I saw grams, I have the molar mass. And I don't see anything else up there based on the 3 questions that we have so far that we should be asking ourselves. And so I have everything I have. So as usual, we draw a line. We draw another line. And we start with our measured number. What's our measured number? Our measured number is right here. There's our measured number. I mean, it's something we threw on a scale, so it must be measured. So we start with our measured number always. Don't ever start with anything else other than your measured number. If you start with something other than your measured number, you may get it right now and then, but most of the time you're just asking for trouble. So there you go. I've got the measured number. There it is. I put it up there. Now, what comes next? Well, what comes next is whatever matches with the units. What do we have here? Grams aluminum oxide. That's what needs to go right there. It's grams aluminum oxide. Where do I see grams aluminum oxide? I see it right there. And so that's what's going to have to go over here. And so I go, and I'm going to have to flip it. And so I go mole aluminum oxide for every 102.0 grams aluminum oxide. Do y'all see how that works? You set everything up so that units cancel. Units cancel. Units cancel. I'm left with moles aluminum oxide. What am I looking for? Moles aluminum oxide. And so now I have something I can put in my calculator, and I go 14.6 divided by 102, and I get an answer. I get a calculator answer, 0.14313 blah 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 something mole aluminum oxide. Now what do? I have to go by significant figures, and so I have 3SF here, I have 4SF here, and so the answer should be the least number of significant figures, which is 3. So my answer should be 1, 2, 3. Look, one more over. We don't have to round, and so that is 143 mole aluminum oxide. There it is. Let me see. Let me make this 3 look a little better. And there it is. There's your answer. So 14.6 grams of aluminum oxide is 0.143 moles aluminum oxide. And we can, of course, go back and forth between grams and moles using our molar mass. All right, now we're going to put all of this together now, okay? All this is going together. Now, let's take a look at my favorite balanced equation. We have 4 aluminums plus 3 oxygen gases go to 2 aluminum oxides. Now I'm going to remind you what this means. This means 4 mole. This means 3 mole, and this means 2 mole. That's what, when we're saying a balanced equation, we're really saying 4 moles aluminum for every 3 moles oxygen gives me 2 moles aluminum oxide. Most of the time that's what we mean when we have a balanced equation, okay? That's what we mean. Just like if we have just one molecule, we mean for every 1 mole aluminum we have 2 moles aluminum oxide. For every 2 moles aluminum for every 1 mole aluminum oxide, 3 moles oxygen for every mole aluminum oxide, and so forth. Okay, so let's put this whole thing together here. So we're going to figure out what's really important, which is if we're doing a reaction and we have so many grams of stuff, I want to know how much I'm going to end up getting. If you're working in a factory and you're making millions of pounds of something, you want to have a pretty good idea how much you're making. So this is the calculation that we're going to do. So how many grams aluminum oxide from 47.8 grams aluminum? And we have the balanced equation up there. And our balanced equation, by the way, is what we're going to use for our mole ratio. So let me erase these guys up here first before we continue. So I'm going to erase these. So we have a balanced equation. I have a problem here. I have a question. All right. Now we have multiple questions that we can ask ourselves and multiple things that we can pull out of this equation based on the answers to our equation. So first off, do I see molecules or atoms? Number of molecules and number of atoms, and the answer is no. So we don't need 6.022 times 10 to the 23rd per mole. Rarely are you going to need that. Okay. The next thing is, do I see grams anywhere? Do I see grams? And I look through my problem, and you have to look physically through the entire problem. Do you see any grams? And I do. I see grams aluminum oxide. And you know what? I also see grams aluminum. The answer to your question can be more than one. It can be none. The answer could be no, I don't see any. The answer could be yes, I see one. The answer could be yes, I see two. You could see three. You can have a yes answer more than once. And we do here. I see 2 grams. Now they're completely different grams, and I go to my periodic table and I say 2 times 27.0 plus 3 times 16.0. I got those numbers from the periodic table, and I say 102.0 grams aluminum oxide for every mole aluminum oxide. And I look over here and I see, you know what? There's another grams, and I say I look on my periodic table. I have grams aluminum for every mole aluminum. Now I got both of these I got off the periodic table. Keep in mind, aluminum oxide is not the same thing as aluminum, and aluminum is not the same thing as oxygen, aluminum oxide or oxygen. Now, so I've asked myself 2 questions so far. I've asked myself, do I see number of atoms, number of molecules? No. Do I see grams? Yes. 2 places. I have the molar masses. And the third question I'm going to ask myself is, do I see myself going from one thing to another thing? And the answer is, why, yes, I do. I am going between aluminum and aluminum oxide. So I need the mole ratio between the two. What's the mole ratio? The mole ratio in this case, remember what I said, this is 2 mole aluminum oxide, and this is 4 mole aluminum. That's moles to moles, so I would say 4 mole aluminum for every 2 mole aluminum oxide. I'm going from one thing to another thing. It doesn't matter what those two things are. You just have to say, well, how many moles to each do you have? And we use our balanced equation up there to get our mole ratio in this case. Someone's waiting in the lobby. Hold on just a second, everybody. Hold that thought so I can let this person in. I don't know. There should be a way I can do this without, without having to leave what I'm doing. So let's see. So let me make sure I'm sharing again. Share content. There it goes. And back to what I was talking about. Here we go. Okay. So I've asked myself all the questions that I can ask as far as doing these stoichiometry problems. Okay, so I've got 2 molar masses and I have a mole ratio. Now what? Well, like we do in all our problems, we draw a line, we draw another line, except this time the line needs to be pretty long. We start with our measured number. Where's our measured number? Here's our measured number right there. Measured number. There it is. And so we start with our measured number, and that is, what's our measured number? 47.8 grams aluminum. Notice I don't care about the problem anymore. All I care about is the numbers. That's all I care about, and the units. And so I always start with my measured number, and now what? Got to match units. That's all you have to do at this point. Once you've pulled everything down, it's all about matching units. And so I match units. I find grams aluminum, there it is right there. I have to flip it over. Moles aluminum for every 27.0 grams aluminum. I've got a check mark by it now. This ended up right there. Now what? Well, I need to find moles aluminum. Where's moles aluminum where I have not checkmarked? I've already checkmarked over here. Don't want to reuse it, but I have moles aluminum over here. There's my moles aluminum. And so this is going to go over here. Except I'm going to have to flip it over though. And so I say 2 mole aluminum oxide for every 4 mole aluminum. Put a check mark. You don't want to reuse things, so let's put a check mark over there. And now I look here and I see moles aluminum oxide. That needs to go over here, because remember, we're matching. It's all about matching at this point, matching and canceling. And so I see moles aluminum oxide over here, and it's already on the bottom, so I can use it like it is. And I say 102.0 grams aluminum oxide for every mole aluminum oxide, and we're done. Now, you should always check yourself. Look, grams aluminum, moles aluminum, moles aluminum, moles aluminum oxide, moles aluminum oxide. What are we left with? Grams aluminum oxide. What are we looking for? Grams aluminum oxide. So I know it's set up correctly. Like I said, don't jump to the setup. You have to pull down the pieces that you need based on the answers to questions. So I put this on my calculator. 47.8 times 2 times 102 divided by parentheses 27 times 4. By the way, it's everything on the top divided by everything on the bottom, because it's a big fraction. It's a big fraction. And I get 90.28888 grams aluminum oxide. All right, and we need to do significant figures on this. And so we look through here at significant figures. We have 3SF, we have 3SF. I have counted here, and I have 4SF here, so our answer should be 3SF, and that is 90.3 grams aluminum oxide. And the way we did it was 1, 2, 3, and we looked one more over. We rounded up the 2 to a 3, and there we go. We have our answer. And so we're going to do more of these. So what we're going to do now is we are going to take a break for a few minutes here. So I'm going to stop sharing and I'm going to stop recording.